Hello and welcome to
Small Talk
about the big issue.
I'm Lorraine.
And I'm Kiara.
We are so pleased to have you back for a very special episode
On global warming. The way this episode is going to be structured is that there's going to be a first part about the scientific basis of it all, how warming happens and what is the science behind it.
Yeah.
And then
a more in-depth analysis of one of the methods that allows us to track global warming. And I'll be presenting specifically a very recent article, so you won't have read this in your newspapers yet, and hopefully giving you a bit of insight as to how science works.
So let's get started.
Yes, let's.
So the subject of this episode is warming. What does it mean? Well, facts are pretty clear by themselves. The years keep increasing in their global average temperature. 2024, for example, was the warmest year recorded since we started recording temperature since the pre-industrial era. It even broke the 2023 record. Now we've reached 1.5 degrees Celsius of global warming, which is what governments wanted to mitigate in their Paris Agreement.
Wait, so if I ask for clarification here, Kiara, 1.5 is the global average of increase in temperatures compared to before the Industrial Revolution.
Absolutely. And the question, you might wonder, why do we care about the global temperature? Because, of course, temperature is completely different all across the globes. And there will be parts where it will be colder, parts where it will be warmer. So looking at the global temperature just is an indicator of the fact that it is warming in more places than it is cooling. That is, the average of our Earth's temperature is rising. It doesn't have to happen in a uniform way, but overall, there are more places getting hotter than there are places getting colder.
Okay.
So that's basically what the average Earth temperature tells you. And it's not also only the land. Oceans have also been getting warmer. So 1.5 is just an average. It doesn't mean that it applies to everywhere. So yeah, that's just something to know when you hear about these numbers. They might seem small, but at the scale of a planet, this is crazy. But we'll get back to it later, more in depth.
Yeah, I think that's a really important point to make.
I think it's important to discuss also how warming works, because most of us have had science classes in high school teaching us about the greenhouse effect. But I think it's good to start from scratch and explore why we can even live on Earth. What makes our Earth habitable? Exciting, right? Because we're, as we know, the only planet where life is sustained. So what happens is that we receive solar radiation from the sun, which warms up our planet. So our planet will either refract this sunlight or it will absorb it, which will warm the Earth. But then it will also re-emit some of that heat, and that's the infrared radiation, which we care about. And that infrared radiation, without our atmosphere, would just be released into outer space. We wouldn't see it again. And that's not enough to keep us warm. I mean, if it was only the sun and us, we'd be freezing. Thankfully, we have greenhouse gases that are naturally present in our atmosphere. So what they do, they're completely neutral towards solar radiation. They let it go through, reach out our Earth. However, they absorb infrared radiation that our Earth emits in return. And then they scatter it into the atmosphere, which allows us to stay warm because they reflect it back to us. So more easily said, the greenhouse gases act in a way like a blanket around our Earth, which keeps the warmth in and allows us to stay warm.
That's a really good analogy.
Yeah. Do you know, Lorraine, how cold it would be without them on Earth?
I don't know. Temperatures near outer space, I suppose?
Actually, it would be 33 degrees colder, so it's not that dramatic, but it would be minus degrees, because right now I think our average temperature is around 14 degrees Celsius, so it'd be minus 15.
I was going to say, the implications of that are crazy because don't you need liquid? Isn't one of the requirements for life liquid water? So if you consider that the average temperature would be like minus 15, basically, then that would mean that most places on Earth would not have had life.
That's exactly it. This is something to know when you talk about greenhouse gases and climate change. Greenhouse gases aren't inherently bad. We need them, actually. Without them, we couldn't be here.
That's a really important point. I think they're often talked about in this very negative way, and I'm sure you'll get into why they can be negative. But fundamentally, they're what keep us alive, and I think that's super interesting.
Yeah, and one of the most important ones is actually the most forgotten one. It's water vapor, because naturally it is responsible for 70% of natural greenhouse effect. So it is thanks to water vapor that we have an atmosphere that keeps us warm. But yeah, so other greenhouse gases I think that are worth mentioning are of course carbon dioxide, methane, nitrous oxide, ozone, and some chlorofluorocarbons. I think for the next part of this episode, I'd like to take you back on a little trip down the history of our planet, which was formed 4.5 billion years ago. And back then, I didn't know this, but I learned it while preparing this episode, that the sun shone 20 to 40% less than it does today. So the Earth received a lot less energy from the sun than it does now.
Wait, is this because of the sun being less energetically powerful then, or is it the atmosphere composition changing?
Oh no, it is the sun having a less powerful intensity, because the sun is a star and they also evolve through time. I mean, at some point our sun is going to explode. We don't have to get into this now. But anyway, so back then the sun's intensity was very much lower than it is today. What do you think the temperature would have been on Earth back then?
Are we talking like when the Earth was first formed?
I mean, yeah, early days of the Earth.
Okay. Here's the thing. I know the Earth was like a hot lava field. So I'm inclined to say that it would have been quite warm, but based off of what you're saying about the sun, now I'm thinking maybe it's cold.
Actually,
so I'm a bit torn between two extremes here.
No, it's really interesting because you're really close to the truth, because even though the sun was actually very weak back then, because of all the gases that were trapped during the formation of the Earth, they were trapped in the mantle, there was a lot of volcanism, a lot of eruptions, and it released a lot of carbon dioxide into what became our first atmosphere. So back then, the carbon dioxide concentrations were incredibly high, and this allowed Earth to have like a first atmosphere that was pretty warm. But then the very first photosynthetic organisms helped decrease that carbon dioxide concentration, and at the same time, the sunlight's intensity kind of increased, and the result of life on Earth and the fact that we have habitable temperatures is due to this crazy coincidence that the sunlight's intensity increased as the carbon dioxide concentrations decreased in our atmosphere.
I think it's super cool to think as well that plants and like living things have impacted the concentration of our atmosphere. Like it's not just, a planetary thing at this point. It's also individual cells pumping CO2 in and O2 out. Yeah.
And they created entire ecosystems. So as soon as they appeared, the atmosphere's composition started to change, leading to the composition that we have now, which is 78% of nitrogen, 21% of oxygen only, and 1% of argon if you remove water.
Is CO2 super low then? I would have expected.
Yeah, CO2 is said to be responsible for 80% of global warming. It only makes up 0.03% of our atmosphere. That's wild.
That's crazy. Yeah. That means it's super potent, I guess.
Yeah, it means that even incredibly small increases in its concentration have dramatic consequences.
Yeah, that's why it's discussed so much.
Absolutely. So Going back to our problem, our big issue. Now, what's the problem? We have a very strong increase in greenhouse gases, which in turn increases the greenhouse effect. And this increases the warming of both lands and seas. And in further episodes, we'll go into what that means for us, for our ecosystems. But overall, what we can say is that the blanket just got a lot thicker. And in a way, it is not the temperature, which is problematic because there's been highs, there's been lows. I mean, the Earth is very old. It's seen a lot of climatic fluctuation. However, the rate at which it is warming is very concerning. We have increased in 1.5 degrees Celsius since the Industrial Revolution.
Which, for context, the time point for the beginning of the revolution is like 1778, I think, when the steam engine was perfected.
Yeah.
So that's like barely
anything.
2,500 years.
Yeah, in comparison to 4.5 billion years. Yeah, actually, the average increase is 1.2 degrees since the Industrial Revolution, but now in 2024, as I said, we reach 1.5 degrees. So it can only grow now in the coming years. And 2/3 of it have happened since 1975. So it's in the last 40 years, which is very disturbing. And it used to take 5,000 years to warm by 5 degrees. But now at this rate it's progressing 20 times faster.
So the issue is, if I understand correctly, not the fact that it is warming, because as you've mentioned, the Earth has known very warm periods and it's been fine. It's the scale at which it's warming.
Absolutely.
And the speed.
The speed, the rate. And I mean, this is also a subject for another episode, but this rate is problematic because it has an impact on all living organisms. The rate in which it is progressing is too fast for most organisms to adapt. Usually it's been spanning across millennia, where species have been able to, come up with adaptations. It's all selection, natural selection. But nowadays it's all going so fast that barely any species is able to keep up.
You're teasing episode 2.
Yeah, sorry. So I'll just finish this scientific part by addressing a question that you may have regarding why we're talking about global warming and not climate change, because these are two terms that are frequently used nowadays. And I think it's good to know what they mean and how they differ. So global warming is just the overall increase of temperatures on Earth, whereas climate change is the impact that those changes in temperatures have on our climates, meaning rainfall, winds, storms, any climatic events. So yeah, I think we're done with the first part of this episode regarding the science behind this warming, and I hope we've made it a little bit more clear.
Yeah, I've learned stuff. I was going to segue into the second part by saying, Kiara, I think you've done a really good job of explaining this global, very complex phenomenon that's influenced by a lot of parameters, and maybe there's some stochasticity or randomness involved. And I think it's really interesting that a lot of the ways that we have of tracking global warming involve atoms, which is like the smallest scale or one of the smallest scales we can look at. And what I've done for this section of the episode is that I've done a bit of a deep dive over the past few weeks.
How exciting.
On ice cores.
Oh.
So Kiara, I wanted to ask you, do you know what an ice core is?
Yes, I think we had to learn about them in geology sometime in high school. I remember my teachers calling them carrots.
Yes.
So I remember those really long icy carrots, but I need you to tell me what precisely you can find inside.
Okay. I can give a refresher, but basically you're right. An ice core is just this really long tube or carrot of ice that you usually drill vertically into these very thick layers of ice that you find around the world. So the most kind of exciting ones are in Greenland and Antarctica, but there's also some in glaciers. I know there's like a Mount Fuji project, so really you can core quite different types of ice. But the premise of an ice core essentially is that snow will be compacted into ice over time. So right now, Kiara and I are both sitting in our studios in front of a desk. And if you imagine snow falling on your desk, eventually the layers at the bottom will compact into ice
Under the weight.
Of the layers at the top. And so this is particularly interesting in areas where there's been snow for a long time. And that's why Greenland and Antarctica stand out so much, and especially Antarctica, because there's evidence of there being snow in Antarctica, potentially for millions of years. So that's really exciting.
So it's kind of like a time machine. You can just go back in time by looking at the oldest snow that you can find in that carrot.
Yes, exactly. It's like layers. Like if you think of, the rings of a tree, it's kind of like that, but on a plane surface, so on a flat surface.
Okay. So at the bottom, you'll find the oldest ice.
Yes, exactly. Most of the time.
Okay.
Hold on to that thought. Now, before I go into detail about ice cores, Kiara, could you guess wildly how long the longest ice core is?
Oh, I know that it's a big struggle, like going deep into the Earth's core, because
it really is.
At some point, the temperature, I don't know if it's the temperature, so I think it's the temperature, the pressure, everything just works against our modern tools.
So exactly.
I would want it to be like really deep so that we get a lot of information about a lot of climates, but I don't think it would be anything more than a couple 100 meters.
It's 3 kilometers. 3 kilometers is the deepest we've dug into ice.
Crazy.
It's crazy. And the ice at the bottom, so this was in Antarctica around the turn of the century. It's 800,000 years old. Neanderthals were around at the time this ice was formed.
Wow.
It's crazy. It really is a time machine. And wait till I tell you everything we can know from this ice.
I'm hooked.
So now, second question of our little guessing game. Do you want to guess how old the oldest ice core is? Because the longest ice core is not the oldest, and I'll explain why.
Oh, you mean oldest as in the age of the oldest ice inside, or the time it was extracted?
I mean the oldest, like how old is the bottom layer of the ice core?
So it's not 800,000 years.
No.
It's more than that.
It's more than that.
Oh, I'm completely clueless.
It's 2.7 million years old.
Wow.
Which is insane.
But how could that happen? Because it's not the longest one. I need to know.
Yes. Essentially, what I've described so far is that you dig vertically down into the ice. And as you've mentioned, this comes with some challenges and potentially limits how old the ice you can access is. But recently, and this ice core was cored in 2019, so it's really recent, scientists have discovered what they call blue ice in Antarctica. And this is kind of rare ice in the sense that it covers 1% of Antarctica. And instead of falling on a flat surface, as I've described before, it falls on a tilted ridge. So if I take that table analogy, it's as if one side of the table was stuck on a stack of books or something. And what that means is that the oldest layers are actually really close to the top compared to the youngest layers of ice because they're tilted. So you can dig not vertically, but at an angle, maybe not quite horizontally, but somewhere in the middle. And that means that it's a lot easier and you can access really old ice more easily.
Okay, that's super interesting. Wow. So what does that ice tell us? Because it's amazing that we can go back that far.
Okay, so I can tell you what the use of ice cores is. Essentially, ice cores are really important and fascinating because we can use them as paleothermometers. Paleo just means really ancient. Thermometers as in to measure temperatures. And essentially, when you think of the history of the Earth, kind of as you've given context for, we've started measuring things like the temperature or CO2 concentrations fairly recently. Like CO2 concentrations we started measuring in the 1950s. So we actually have no record for what happened before, and this is really important to understand what's happening now, to give context to the kind of warming we're seeing now. And so ice cores are what we call proxies, and I think this is a really important scientific term. I think it's definitely used in biology, but I'm pretty sure other sciences use it as well. And a proxy is a method by which you measure one parameter as an indirect measure of another. So we can't go back in time. Ice cores are kind of time machines,
sadly,
as you said, but not that, but not that kind of time machine. And so it allows us to assess what the temperature and climate would have been like in the olden days.
Absolutely, yeah.
And so we know that it works. We've been able to confirm that it works because right now the youngest ice that we have access to in areas where there's high snowfall in Antarctica is about from the 1980s. And so we have CO2 and temperature measurements for that time. And so we can cross-check and see, actually the things that we're measuring in the ice cores do correlate to temperature and things like climate that we've recorded.
Yeah, that's super important to make sure that what you measure actually is representative of the reality of the climate back then.
Exactly. And you can also look at ice cores from different areas and see, okay, they match up.
Okay.
So this is pretty established techniques. And now, you're probably wondering, what exactly are we measuring in this ice core? Air bubbles, they're trapped in the ice. And this can be used to determine what the global climate would have been like, because a lot of the greenhouse gases that you've mentioned stay in the atmosphere long enough that they can be mixed homogeneously around the globe. So yes, we're coring ice from Antarctica, but actually it's giving us information about what the entire Earth on average would have been like.
Wow.
So it's super interesting.
Because those bubbles they kind of contain some sort of time capsule of what the atmosphere was like
Exactly.
back in those days.
Save for one thing. So usually proxies come with limitations. One of the limitations of ice cores is that there's actually a slight discrepancy between the time of the snowfall and the ice bubbles that will be formed in the ice. Because while the snow is still in snow form, air can diffuse through it. It's only once it's fully kind of solid ice that the air bubbles will be tight and not leaking. Now, if you think of the kind of broader variation in climate that we've seen kind of over time that's not human driven, you wouldn't expect this to be too big of an issue because we're seeing very slow variation. So even if it takes 100 years for that air bubble to form, then it's still going to be representative of what the climate was like. But I would expect that this becomes more problematic when we're seeing very fast warming like today.
Okay. Yeah.
So I don't know what that means for the future of ice cores or how we're going to be interpreting them in the future. And the second component of the ice cores that we look at is the actual ice. Have you heard of isotopes, Kiara?
Yes. I had to learn about them in chemistry in my bachelor's degree, and they're really interesting because they can have so many uses and like climate change and everything. Because from what I remember, they have different amounts of neutrons. Basically, they're alternatives to atoms that we have, except that they have some sort of signature that makes them differ from the ones that we're usually around.
Exactly. So if you stick with us while we go through just a teensy bit of chemistry, most atoms are composed of protons and electrons. Protons have a positive charge, electrons have a negative charge. And most things that you'll come in contact with today have an equal number of each. And that means that the what you're touching isn't charged. However, there's a kind of third class of particles that's called neutrons, which is what Kiara was talking about. And these don't have a charge at all. And so there's more flexibility in terms of how many can be in one atom. So what we're looking at in ice cores are oxygen molecules, so in the water of the ice, that have either 8 neutrons, and this is called oxygen 16, because you've also got 8 protons, or oxygen 18, which has 10 neutrons.
Mm-hmm.
So what characterizes these oxygen 18 molecules is that they're slightly heavier.
Yes.
Now, the weight of a neutron, if you're dying to know, is 1.6 times 10 to the power minus 24 grams. So it's if you put 0.23 zeros, 16 gram. I tried to give an idea on a biological scale, like how many times you would have to cut up an ant to get a neutron. It's like not really comprehensive, but it's very, very small, but it still makes a difference. And importantly, isotopes are stable. So it's not like radioactive material that will decay and change over time.
Mm-hmm.
If you're an oxygen 18 molecule, you're staying
there.
an oxygen 18
Okay.
molecule.
But so how can we use this to tell us about the climate?
So what we look at is the ratio of oxygen 18 to oxygen 16 in the ice.
Mm-hmm.
Now let me walk you through the path of water from the tropics, where there's a lot of evaporation in the ocean, for example, to the ice. So oxygen in the water, water is made of hydrogen molecules and oxygen molecules. So you've got oxygen being pumped from the ocean into the clouds. And now because you've got some oxygen 18 that's a bit heavier, it's harder to pull it out from the water. So in general, in clouds, you've got more oxygen 16. Now, in a colder climate, you're going to have more precipitation. And what happens is there will be some oxygen 18 in the clouds, but they're the ones that are going to precipitate first. So they're going to fall back in the sea.
So precipitation meaning
rainfall, for example.
Or snowfall, actually.
So in this case, let's think of, okay, the water is pumped up from the tropics into the clouds. It falls a bit as rain over water, goes back directly into the ocean. Over land, it ends up going back directly into the ocean. And by the time it's reached the poles and it's snowing, it actually has very little oxygen 18 because it's been lost over the course of its travel from the tropics to the...
Because it was the heaviest, so they were most likely to go down earlier.
Exactly. So what we find is if there's a colder climate, there's going to be more oxygen 16 compared to oxygen 18 in the ice.
Okay.
Because that's how much will have traveled all the way to the pole. In a warmer climate, you get the opposite. There will be more oxygen 18, well, not more oxygen 18 than oxygen 16, but the ratio will be higher of oxygen 18
That's
to
incredible.
oxygen 16.
So to sum up, those ice cores, they give us time capsules into like the atmospheres of thousands of years ago, and they also allow us to measure the oxygen 18, oxygen 16 ratio, which tells us how warm, how cold it was back then.
Exactly. If I can add a tidbit of biological fact as a slight bias here.
You may.
Really interestingly, the shells in the ocean, because shells will also take up oxygen from the water, they show the reverse pattern than the ice cores do. So they'll show more oxygen 18 in colder climates and less in warmer climates.
How can that be?
Essentially, when you've got a colder climate, more of your oxygen 16 is locked, if you will, in ice. And so the proportion of oxygen 18 to oxygen 16 in the water is higher than when you've got less ice. And so you've got more oxygen 16 to dilute the oxygen 18.
That makes a lot of sense. Yes. It was a great explanation. And I remember learning about this now. You're giving me flashbacks from high school. But I thought it was really interesting. Yeah. Wow. So much to learn from ice cores.
I know. There's really so much to cover. What if I summarize the kind of major findings of ice cores so far? It's that we've been able to track the carbon concentrations over the last, for example, thousands of years. And we see that it's starting to rise from the 19th century.
Okay.
they're now nearly 40% higher than they were before the Industrial Revolution. And also linked to what you were saying about the speed of the warming increasing earlier in the episode, it used to be that it took about 200 years to get an increase of carbon concentration in the atmosphere to 15 parts per million. Parts per million is just a measure of carbon concentration in the atmosphere.
Yeah, it just means that for a million molecules in the atmosphere, there's going to be 15 of carbon dioxide.
Yeah, and this is linked to what you were saying earlier, that carbon is really in low abundance in our atmosphere. Yes. But now it takes that same amount to get 15 more parts per million in 6 years.
Wow.
So what we're seeing is there's a lot of carbon being pumped into the atmosphere in very much artificial, human-driven ways.
So what used to take 200 years before now takes 6 years?
Yes.
Wow.
And this is because of burning of fossil fuels, mostly.
Yeah.
But also the fact that we have less land that's covered by plants to pump out CO2 from the atmosphere.
Okay.
So this is why it's important to protect things like forests, for example.
Yeah. So many things to get into our next episodes.
I know. There's so much to cover. But yeah, anyways, that was a very long introduction to ice cores. I think I went down a bit of a rabbit hole in my research, but it was really interesting and really multifaceted. The article that I want to present today is called The Quandary of Detecting the Signature of Climate Change in Antarctica. A quandary is not a scientific term. It's just like the issue or the problem.
Okay.
And it was published in 2023 by a research team led by someone called Mathieu Casado.
Okay.
I'm pronouncing his name with a French accent. But I assume he's French because actually part of the research team was based in France.
Oh. So tell us, what made you choose this article? What is there to learn from this, and what makes it exciting to read?
So I chose this article because it's really good illustration of what we can do with ice core research. Okay. So we can, of course, look at individual ice cores, but this article looks at 78 different ice cores.
Okay.
And it does that to study something that's called polar amplification. Polar amplification is the process by which the poles will warm faster than the global average. So we touched on this earlier when we said, not every part of the globe is going to warm evenly. Actually, the poles will warm faster. Now, there are a lot of reasons that this happens. I'll just go over a few of them. But essentially what happens when the poles melt, even just a little bit, is that land surface goes from being white to being darker because it's the color of the sea.
Yes.
I think you can infer based off of what you presented in the beginning what the effect of that might be.
This is the albedo, right?
Yes.
The albedo of a surface is the amount of the sunlight that it reflects compared to the amount that it absorbs. And of course, a whiter surface will reflect much more light than it absorbs.
Yeah.
Whereas darker surfaces like the sea, plants, dark green, dark blue, they absorb a lot more energy and then release infrared radiation, which in turn heats our atmosphere. Usually, ice has a very high albedo, which means it reflects a lot of the sunlight. But when it starts melting, it's replaced by land, which is usually darker and will absorb a lot more sunlight, making it warmer. So it has a lower albedo. So overall, the melting of the ice contributes to the warming of the planet because of decreased albedo of the planet's surface.
And I'll explain why this is especially important in the poles. Now, not to make maybe a tragic pun here, but this snowballs into a lot of different things. One of them is that as you get more water coverage in the tropics, you get more evaporation. And Kiara, as you mentioned, water vapor, huge greenhouse gas. So you get more warming happening there.
Absolutely. It's a big, how do you call it? A positive feedback loop. The more water vapor there is in the atmosphere, the more warming there will be because it's a greenhouse gas. And the more warming there will be, the more evaporation you'll see at the poles.
You also get, as there's more water vapor, more cloud formation. And clouds are really good at trapping heat. That's why in winter, if there's cloud coverage, it will typically be warmer than a sunnier day in winter because the clouds are really good at trapping heat. So really, you can see that everything is quite linked and things will easily kind of lead to one another and create this, positive feedback loop, as you said.
Yeah.
Now, if I go back to polar amplification is quite understood in the Arctic, so in the northern hemisphere, but actually not so much in Antarctica. And there are a couple reasons.
Mm-hmm.
One is that, obviously records in Antarctica are sparse. The history of Antarctica exploration is really interesting for reasons that aren't really linked to climate science. But
I can imagine, yeah.
But essentially, yes, we have few records of the metrics that we use for climate change in Antarctica. And we're using proxies most of the time. But also, there's high variability in the Antarctica climate that's natural.
Okay.
So it makes it more difficult to find trends in the data that we have. And I'll come back to this later. But first, I want to make the point that it's really important to understand polar amplification, maybe for two main reasons. One is that, the poles are natural habitats. They host loads of organisms. You might think of penguins and seals, but they're also really cool algae living in Arctic and Antarctic lakes.
Absolutely. A lot of endemic organisms that rely on those ecosystems.
Mm-hmm. So it's really problematic that we're seeing less ice cover, but also if Antarctica melts, we want to know because that would have a huge impact on sea level rise, for example.
Mm-hmm.
So it's really important to understand the climate in Antarctica and how it might affect the melting. And now, how do we study polar amplification? Well, we can use isotopes and ice cores. So what this study did is that it looked at 78 different ice cores from Antarctica and looked at the records over the past 1,000 years.
Yeah.
And they showed evidence of polar amplification. Now, interestingly, other research groups had tried to do something similar, and they hadn't really found evidence of recent global warming in ice core data. Now, we know that the Earth is warming, so why aren't we finding global warming in the ice cores? And the authors of this paper argue that it's because of the large natural variability in Antarctica climate. And now I'm not a climate scientist, but the main factor of this variability is a phenomenon that's called the Southern Annual Mode.
I think I might have heard of it in an oceanography course when I was in Norway. But there's so many different wind patterns, and they all have such a big impact on the climate, and they can explain so many phenomena. Like, for example, the fact that here in Lund it's not minus 20 degrees thanks to the Gulf Stream, whereas at similar latitudes we would be in Canada, I think, across the ocean. The climate is much colder. So all of that is thanks to oceanic currents and winds, which are all interconnected.
Okay, yeah, I did not know that about Sweden. But yeah, essentially there's something very similar that happens in Antarctica, where this Southern Annual Mode is a pattern of wind that will determine in large part the weather conditions over Antarctica. So it will bring either kind of clear weather or very stormy weather, which comes with more precipitation, for example. And importantly, this Southern Annual Mode changes naturally over decades. So sometimes it'll bring, there'll be long periods of time where it brings more clement weather and others where it brings more stormy weather. So what the authors did is that they looked at what's called a persistence metric. And a persistence metric is a statistical analysis that they use to identify long-term shifts in climate variability in Antarctica. And importantly, it's a metric that's really resistant to statistical noise. So, for example, randomness in this case, just the natural variability of the Antarctic climate, which is quite high. And so that makes it a lot harder to find a clear trend. And what they found is that if you use this persistence metric, you can find evidence of polar amplification starting 50 years ago.
Okay.
So what they found concretely is that there's a change in the dynamics of the system they were studying. So if they correlate isotopic concentrations and CO2 concentrations, they find that there is a link, but it's quite weak.
Okay.
So it doesn't explain a whole lot. But if they correlate change of persistence and CO2 concentrations, they find a really strong positive link.
Change of persistence, could you explain what that means?
Change of persistence is this statistical trend that they're able to see in their data.
Okay. So that's the tool that helps them connect the dots and get rid of the noise and find some actual evidence that the Antarctic is warming.
Exactly. Yes. So what that correlation shows, now correlation is not causation, but as I think lots of students worldwide are told very often, but what they stipulate is that means that the changes in the system they're seeing may be attributable to CO2 concentrations. Now, the second step of this analysis is to do what's called a spectral analysis.
Okay.
A spectral analysis is another statistical method that allows them to quantify the signal to noise ratio of their data. So what that means is that they can use it to detect how much of the variability they see is meaningful, so how much of it is humans inducing warming versus how much is natural variability.
Okay. That's actually a really powerful tool.
Yeah. The statistics on this article are quite impressive. And what they show is that the trend that they're finding goes outside of the natural variability.
Okay.
So what they show is that 50 years ago, there's a disruption in the general systems, and the isotopic ratios change in such a way that indicates warming.
Okay.
They show that is strongly linked to CO2 concentrations, and they show that this is outside natural variability.
Wow. And this, no one had managed to prove that for Antarctica before, right? That was always the conundrum, why ice cores couldn't show warming there? Or did it explain why it was so hard to quantify before?
It kind of both. It explained, okay, we're not taking into account natural variability properly, but also it showed a phenomenon we knew existed.
Okay.
Because if you just measure the temperature in the South Pole, you'll see that it's maybe warming faster than in other areas.
Of course.
The last bit, and I won't go into too much detail here, but they compared their results to existing climate change models, notably CMIP-5, which is a really important climate change model because it's one of the ones that's used for the IPCC. Now, I think we will do an IPCC special episode.
Yes.
IPCC.
Let's keep it simple. What is IPCC? Tell us.
It's the Intergovernmental Panel for Climate Change. And it's one of the main scientific authorities that influences, or that informs rather than influences actually, that informs policies worldwide.
Yes, they do. They summarize all the research that's been done on climate change and look at the impacts on us, on ecosystems, and they release really big reports, I think every 7th or 8th year.
So they compared their results to the factors that CMIP takes into account to make its predictions, and they showed that it underestimated polar amplification because they weren't taking into account natural variability of the Antarctic climate properly.
Which means that reports like the APCC are underestimating the rate at which Antarctica is warming.
Potentially as an indirect consequence, yeah.
That's wild, yeah.
So this article was able to kind of determine a new method to analyze Antarctic ice cores, especially more recent samples.
Yeah, and link it to global warming and show that it is happening in Antarctica. I think it's really exciting when such a team comes up with a new way to measure something that has been lacking and that is crucial to kind of give us an idea of the scale of the change and how important it is to act to prevent further increase in temperatures now than later.
Yes. That's all I'll say about that article. And I think we can start wrapping up. But there were a couple resources I thought might be interesting to mention.
Mm-hmm.
During my research, I found that the NASA website, has a lot of really cool, easy to understand resources to explain both climate change, different factors, but also ways that we have of measuring it. There's some really cool images taken from space.
I think it helps you understand how researchers actually proceed, like to take the temperature of the Earth, because of course there's lots of different ways. You don't just stick a thermometer into the Earth. There's like different ways of doing that.
I was going to wrap up by just presenting quickly more recent ways that we have of tracking modern climate, so what's happening now.
Mm-hmm.
And we kind of do stick a thermometer everywhere we can. So that means like there are like tens of thousands of weather stations around the world that are recording temperatures at any given time, but there are also ships and buoys in the oceans that record the temperatures. The ISS, the International Space Station, and satellites take pictures of water bodies, for example, to track, evaporation, how much water a certain landmass has. They can generate heat maps of areas from space. They're studying things like how dust particles carried by winds are going to impact heating and cooling. So we do rely on thermometers quite a bit. And also, I thought this might be interesting for some people listening. The US relies on just regular people and citizens to track the weather, the temperature, and to report it to the National Weather Service's Cooperative Observer Program.
Wow.
And that's also a way they have of tracking climate.
And it's really helpful. I mean, it's precious data that contributes to research on climate change.
Yeah, exactly.
Should we maybe sum up this extra long episode?
Thank you for sticking around for so long. And hopefully you've learned with us. I think it's fair to say that both of us have really discovered some new things.
Absolutely.
In the process of making and recording this episode.
If you have any questions or suggestions regarding future episodes, feel free to comment or send us an email at smalltalk.bigissue@gmail.com. We'll see you in 2 weeks for the next episode, which will be about the consequences of global warming and its impact on climate change.
We have dramatically titled it, Who's Going to Pay the Price?
So stick around if you want to find out. And we'll be waiting for you. We're very excited to have you here.
And goodbye.
We fact-checked this episode and wanted to clarify a few things. I, for one, said that global warming has reached 1.5 degrees Celsius since the pre-industrial era. While global warming is thought to account for a 1 degree increase in global temperatures since pre-industrial times on average, the year 2023 was about 1.3 degrees warmer, and 2024 was confirmed to be 1.5 degrees warmer. However, these are measures for individual years, but the general global warming average across years is likely to reach 1.5 degrees Celsius between 2030 and 2052 if it continues to increase at the current rate. Finally, Lorraine defined a quandary as an issue or a problem. In fact, the Cambridge Dictionary definition of a quandary is a state of doubt or confusion. That's all for this episode. See you next time.